You did nothing wrong.
Oh, I forgot to put this on. Let me do this real quick.
You always recording.
Yeah, you're always on. You're always being recorded. Story of your life, right? Right.
Well, yeah, I got in your phone camera.
Mm-hmm. Yep.
We're talking about.
All right. So everybody found your lesson online last week, I hope. Yes. Okay. Good deal. So hopefully everybody was able to get through it. I was really bummed that I missed that particular lesson because I really like teaching that lesson, especially the music part. Like I really enjoy that. So I was a little bummed that I missed that with y'all. I think everybody was able to get the videos except you, Emma. I'm not sure what happened there.
Really get one because I have this Canopy Parental Control app that has the word root in it, I guess.
Oh, because of his name?
Yeah.
Okay.
So I managed to pull it up on a separate tab on my phone.
Okay. Well, good. I'm glad you got to see it then. All right. Okay, so we're moving on. We're going to get started, and we're moving on, talking a little more about electromagnetic spectrum, which we kind of started last week, and we touched on it very slightly. So we talked about waves and mechanical waves, right? And okay, who remembers our different types of waves? What do we have, Darcy?
There is a. Why is it leaving my mind?
Oh no, Eunice, do you remember?
Longitudinal waves, waves, and surface waves.
Very good. Okay, so what kind of waves were sound waves? Do we remember? Do you remember, Emma?
Longitudinal.
They are longitudinal waves. That's right. Okay, so today we're talking a lot about light. All right, and you'll find that light is interesting because it travels as waves and as particles. So, have we got your binders? We're good to go?
Yes.
I am hoping y'all like today's rats. We got a rainbow theme for today. It's a lot of fun. We got rainbow rats. So here we are, electromagnetic waves. So what's my first word here, Darcy?
Okay. Wait, no, what?
Transverse, but hey, all right.
I was reading the first thing.
You're good. So transverse waves that have some magnetic properties are what electromagnetic waves are. So they're transverse, not longitudinal, and they have some magnetic properties. Okay, and electric properties. So what are we talking about that consists of changing an electric and magnetic field? Yeah.
Electromagnetic radiation.
Yeah, or waves, electromagnetic. Yep. All right. So there's where we are. So we have changing electric and magnetic fields. All right. And then what's this last one, do you think? The energy. That's
Electromagnetic radiation.
That's right. Okay, that's what we're looking for. So electromagnetic waves. You with me, Louis, Nico? So electromagnetic waves have both electric and magnetic fields. And then you've got electromagnetic radiation is the energy that's transferred by those waves. Okay. So what does that mean? Well, we'll talk about it a little bit more here. So how are these things produced? Do you know what that one is, Darcy?
Yes, I believe it hurts.
She's looking. Did she find it? Anybody find it?
Neon? No.
Not neon. What is it?
Is it photoelectric?
Electric field exerts electric force on charged particles within a region of space. We're talking about charged particles.
The old lab that was already in mine. And you told me to change them.
Oh, y'all, I have your printouts. I forgot. You guys needed them, right?
Oh, yeah, I did not. I did.
You did? Okay, I thought someone. You
made us.
You found it?
Yeah.
Okay.
He made us change. Because
remember
you gave us the
lab? Yes. Yes. Okay, that's all right. There's the rest of your quarter because I know you didn't have it.
Thank you.
Okay, so what does it mean when we talk about charged particles? What's a charged particle? Nico?
Have the answers.
Yeah, that's a good way to put it. Okay, so we're talking, well, does a neutron have a charge?
No.
No, so what particles have charges?
Photons.
Protons and electrons have charges, right? So when we talk about electricity, we're talking about electrons primarily, okay? So what exerts a magnetic force? If electric field exerts an electric force, then what's exerting your magnetic force? Eunice?
Me?
Yeah.
Okay. Is it a photon?
Not in this case. So what we're talking about here is we're talking about magnetic fields. So electric fields exert electric force. Magnetic fields exert magnetic force. Okay. So electromagnetic waves. You guys good over there?
Yeah.
Do you need one somewhere or you find it? I was gonna say, there's probably others down in those couch cushions, but I don't know what else is in there. I take no responsibility. So electromagnetic waves are produced when an electric charge vibrates or accelerates. All right, so electromagnetic waves vary in wavelength and in frequency. So electromagnetic radiation behaves sometimes like what and sometimes like what. This is what I was saying earlier. This is what's unique about light. Anybody but Eunice know? Anybody else? All right, Eunice.
Waves and particles?
Right, okay. Sometimes like a wave and sometimes like a particle. All right. Light energy, electromagnetic energy is the only kind that really does this. So it's really interesting because it's different. All right. So we have this guy Young. All right, we're going to talk about some of these scientists in a minute. So Young had evidence for waves. So he's the one who can say absolutely electromagnetic radiation travels as waves because he passed a beam of light through a little tiny slit and then a double slit. So a single slit and then a double slit. And he observed brighter and dimmer bands projected onto this dark screen. So when he was doing that, this was the experiment that proved that electromagnetic energy travels as waves. So that was Young. Young's like, okay, it travels as waves. And then we have another bit of evidence that shows that it travels as particles. This is the photoelectric effect. Okay, who can tell me what the photoelectric effect is? Anybody want to give me a shot? Give it a shot. Eunice, do you want to get? Oh wait, Nico, do you want to give it a shot?
The emission of electrons caused by metal, caused from
Yep.
metal. The emissions of electrons from a metal caused by light striking the metal is
You got it.
caused.
Yeah. So when light strikes certain metal, you get electrons that are emitted. Okay. And when not all wavelengths are going to produce electrons, but some do. And that's how we know that light also travels as a particle. So we know that it travels as a wave and a particle. Now, does sound travel as a particle?
No.
No,
No.
sound travels as a longitudinal wave, right? Right. And how about like physical force? Like if I tap this, there's definitely energy that moves, continues to move through until there's friction to slow it down. Is that particle or is that more like a wave? More like a wave, right? So when your light is different in this respect, and it's important because it makes a lot of the things that we kind of take for granted that we see every day. It's what makes things the way they are. Okay. So somebody said this word earlier. What do you call these little packets of energy? Say it, Nico.
Photons.
Yeah, photons. All right. So photons are these little packets of electromagnetic energy. All right. So is light a particle or a wave? So let's have a look here. And you will see if I can make it go. I don't know if this is going to lag or what, because we're dealing with a whole new situation today. Okay, oh boy. All right, hold on.
We might have to exit.
Yeah, I might. Whoop,
Oh,
there it goes.
Is light a particle or?
Yep, it just took it a second. We're hoping there's not too much of a lag because he just loaded a new program and all this mess. So.
it looks like in depth, not like all brain.
Your eyes and then your brain are collecting all sorts of information about the pencil. Its size, color, shape, distance, and more. But how exactly does this happen? The ancient Greeks were the first to think more.
We hope you enjoy your trial of Air Palette Food.
Oh.
For an uninterrupted experience, purchase Air Palette Food.
That's what he just put on my computer. Sorry about that.
Then to gather information about faraway objects. It took over 1,000 years before the Arab scientist Al-Hassan figured out that the old Greek theory of light couldn't be right. In Al-Hassan's picture, your eyes don't send out invisible intelligence-gathering probes. They simply collect the light that falls into them. Al-Hassan's theory accounts for a fact that the Greeks couldn't easily explain.
Very
why
lots of
it gets dark sometimes. The idea is that very few objects actually emit their own light. The special light-emitting objects, like the sun or a light bulb, are known as sources of light. Most of the things we see, like that pencil on your desk, are simply reflecting light from a source, rather than producing their own. So, when you look at your pencil, the light that hits your eye actually originated at the sun and has traveled millions of miles across empty space before bouncing off the pencil and into your eye, which is pretty cool when you think about it. But what exactly is the stuff that's emitted from the sun, and how do we see it? Is it a particle, like atoms, or is it a wave, like ripples on the surface of a pond? Scientists in the modern era would spend a couple of hundred years figuring out the answer to this question. Isaac Newton was one of the earliest. Newton believed that light is made up of tiny, atom-like particles, which he called corpuscles. Using this assumption, he was able to explain some properties of light. For example, refraction, which is how a beam of light appears to bend as it passes from air into water. But in science, even geniuses sometimes get things wrong. In the 19th century, long after Newton died, scientists did a series of experiments that clearly showed that light can't be made up of tiny atom-like particles. For one thing, two beams of light that cross paths don't interact with each other at all. If light were made of tiny solid balls, then you would expect that some of the particles from beam A would crash into some of the particles from beam B. If that happened, the two particles involved in the collision would bounce off in random directions. But that doesn't happen. The beams of light pass right through each other, as you can check for yourself with two laser pointers and some chalk dust. For another thing, light makes interference patterns. Interference patterns are the complicated undulations that happen when two wave patterns occupy the same space. They can be seen when two objects disturb the surface of a still pond, and also when two point-like sources of light are placed near each other. Only waves make interference patterns, particles don't. And, as a bonus, understanding that light acts like a wave leads naturally to an explanation of what color is, and why that pencil looks yellow. So, it's settled then, light is a wave, right? Not so fast. In the 20th century, scientists did experiments that appeared to show light acting like a particle. For instance, when you shine light on a metal, the light transfers its energy to the atoms in the metal in discrete packets, called quanta. But we can't just forget about properties like interference either. So these quanta of light aren't at all like the tiny hard spheres Newton imagined. This results that light sometimes behaves like a particle and sometimes behaves like a wave, led to a revolutionary new physics theory called quantum mechanics. So, after all that, let's go back to the question, what is light? Well, light isn't really like anything we're used to dealing with in our everyday lives. Sometimes it behaves like a particle, and other times it behaves like a wave, but it isn't exactly like either.
Maybe it's a wave made of particles.
Yeah, right.
Both a wave.
Maybe it's both. So if you're really into physics, quantum mechanics would be your smarty branch there. Yeah, you could spend your whole life studying that, because that's a thing.
Maybe the particles are waves.
Maybe they are. No, well, yeah. So, waves of the spectrum. So, who discovered infrared? Do you know that in 1800? Infrared.
No, I almost like one.
Anybody know? All right, so it was this guy named William Herschel. Okay, Herschel's a cool dude. All right, so he discovered infrared. Okay, now here's a word for you. We talk about Greek and Latin roots being in science all the time, right? Infra. Anybody want to guess what infra is? Do you know? Below. How'd you know that? Ah, good job. You did your reading. Okay, below. So infra is below. So infrared means it's below red and the wavelengths that we can see. You also have infrasound, which is lower than we can hear, right? So if infrared is, so when you think about a rainbow and you start, you know, the whole Roy G. Biv, red being on one end, what's the V?
Violet.
Violet. Okay, so if infrared is below red, we can't see any colors, wavelengths below that, then what is ultraviolet?
Above violet? Above violet.
Above violet. Yeah, a wavelength that we can't see that's above violet. Okay, so they're there. There's all kinds of waves around us that we can't see because they're either higher or lower than what we can detect, but they're there. And some animals can. There are some animals that can sense those particular types of waves that are infra or ultra to us. Uh-huh.
What if an animal is infrared?
What if an animal, what?
What if an animal?
There are some that can sense it. Yeah. And we use infrared.
The color.
Oh, the color? Oh, that animal would probably be invisible to us. So, but we would know it's there. So
Dogs can hear the sound like higher than us. They can hear.
Mhm.
Higher.
they can hear ultrasound, right? That's that. Uh-huh.
Does that mean like it would be possible to make something make an invisible thing if they made a
That's a good question. Could you make something that's infrared and then not see it? That's a great question. Okay,
That's
so
how invisibility is possible in the future.
this is true. All right, so the full range of frequencies. What's this? Let's see, Nico or Lewis? No, Carlos or Lewis. You guys don't have too many coins yet. Anybody want to guess? Do you want to know what's the full range of them called? We put them all together.
Oh, electromagnetic spectrum.
Yeah, there you go. All right, electromagnetic spectrum. Spectrum meaning the whole range, right? So we have a spectrum. And this is going to include things like radio waves, infrared, visible light, ultraviolet, X-rays, gamma rays. So these are all parts of the electromagnetic spectrum. And some of them we don't see, but they're there. Like radio waves are everywhere. They're all around us right now. You can't see them and you can't hear them, but they're there, right? And same thing with gamma and X-ray. Like, you know what X-rays are for, right?
Yeah.
Yeah. Okay. So, now look at the way these are listed. They're listed with radio, then infra, then visible, then ultraviolet. So what does that tell you about radio, do you think? What do you think, Darcy?
Red.
So it's going to be lower than infrared. So lower. So then,
So radio waves have like the longest wavelengths and the lowest
Right.
frequency.
right. So if we think about that for a minute, so radio waves are all around us. Are they harmful? Mm-mm.
Can be.
Well, yeah, they can be if it's, yeah. But in the ones that are all around us every day are not like a major concern. How about ultraviolet? What do you know about ultraviolet rays? Like, where have you heard that before?
It's beyond our eye.
Yeah, uh-huh. Where might you get, completely shut up with ultraviolet rays? Where would you find them? You go ahead, Darcy. Do you want to
You
go?
opened up a black light flashlight and shone it in your eye.
That's one way. How about what causes your sunburn? UV. UV is ultraviolet. Okay.
Skin cancer.
So we know that ultraviolet can cause cancer, too much of it, right? What do you think about X-rays?
X-rays, too much X-rays.
Same thing. So are you seeing a trend here? Yeah, a little bit. Yeah. Okay, so how do these waves travel? So electromagnetic waves can travel through a vacuum or empty space as well as through matter. So electromagnetic waves travel at the same speed, but they have different, what? Eunice said it a minute ago. What'd you say, Eunice?
They have shortest frequency and longest.
Right, different wavelengths, different frequencies, but the speed is the same. Okay, so what's the name of the range for electromagnetic waves when they're placed in order of frequency? Who's got it? Okay, Carlos.
Visible light.
There you go. So yeah, the visible light's the part we can see, but the spectrum, which we said is all the different ones, and when we put them in order, that makes the spectrum. So like a rainbow is a spectrum, but it's always in order, right? You recognize a rainbow, the colors are in order, like they are right here on this little guy's shirt, right? So
It really annoys me.
it's ordering
when
them.
not in order.
So visible light's what you were going for here, Carlos. So only a small portion of it is visible light. So we only see a little bit. So if we were to do math, this is the way we would do it. Wavelength, frequency, velocity. Now, I just said that the speed for these waves is the same. So considering the speed is the same, thinking about this formula, right? V on the bottom. Do you know what this is? Anybody know what that is?
It's a Greek letter.
It is. Do you know what it is?
Yeah.
It's lambda. Okay, so, so if this is wavelength and this is frequency, if wavelength goes up, think about it as a math problem for a minute. What's our relationship here? If this is always 1, okay, just pretend it's always 1. It's on the bottom, okay? Think about these. What? What you get? Go ahead.
Is it, this equals those,
Mm-hmm.
like you multiply wavelength times frequency equals waves?
So if you wanted to find wavelength, you would divide frequency by velocity. And if you wanted to find frequency, you would divide wavelength by, yeah.
Velocity.
Yeah, right. Okay. So we'll come back to it. We'll come back to it later when there's not a bunch of stuff going on. All right. So speed of electromagnetic waves. So we have this guy, Michelson. All right. So he installed this stationary mirror and a rotating octagonal mirror. All right. And he positioned them. He went outside. This is not a lab. He went out and did this in the mountains, positioned them on opposing mountains and used the known speed of the mirror rotation and the distance between the mountains to determine the speed of light. Oh boy, this guy had lots of big ideas, right? Let's go out in the mountains and play with mirrors. That's a lot going on. So let me see if this one will play. I don't know, they're being real kind of weird this morning. Do I do it now?
Do it after the cloud, probably, but it's working.
The speed of light should
Now
only
it's-
be that hard.
It was real.
Light moves with uniform motion
His voice
through a
got
constant
loud.
medium,
For
so we can use the
trying to hear it,
formula
not
V equals
like
d over t. The tricky part is trying to measure t. Because even if you pick a distance that's really huge, like the distance around the entire Earth, the time it takes light to travel that distance is only about 0.13 seconds. So what we need in order for this to work is a very, very good stopwatch. The stopwatch would come from American physicist Albert Michelson, who between 1878 and 1926
I mean, it's much
refined
better
a
than it
method
was.
to measure the time taken for light to travel between 2 points. This is the Michelson rotating mirror experiment. A ray of light from a light source reflects off a rotating 8-sided mirror. Light travels a long distance. In this case, Michelson had it move about 35 kilometers one way through an old abandoned mine shaft between 2 mountains in California. The light hits a flat mirror at the end of the shaft, reflects and comes back through another 35 kilometers, then strikes the rotating mirror again.
We hope you enjoy
Uh,
fun and
Yes, Air Parrot.
for uninterrupted experience. Purchase Air
Sorry.
This isn't on it.
www.airparrot.com.
Quickly
Sorry.
at the observer's eye.
There we go.
Who can only
And how can a
interrupt
spinning
when
mirror
you're
be a
doing
stopwatch?
Yeah.
The trick is that the frequency of the spinning mirror, or how long it takes to make one full revolution, can be adjusted. Starting from rest, the frequency is slowly increased as light shines on it. The light reflecting off the spinning mirror will only be observed if the ray hits the observer's eye exactly. This only happens when the spinning wheel comes into the exact same alignment it was in as when it originally was hit by the light. And because it's an 8-sided wheel, this occurs for the first time at exactly 1/8 of a revolution. The genius of the Michelson experiment is that spinning mirror's frequency can be used like a timer. As long as we remember that it's going to take the light exactly 1/8 of a revolution of that spinning mirror to travel its 35 kilometers one way and its 35 kilometers back the other. Let's look at an example. So let's say that we get the mirror spinning at a frequency of 525 hertz, or 525 revolutions per second. And at that frequency, the observer can see the light. We can convert the frequency into a time measurement by using the formula period equals 1 over frequency. The t in this formula is period, or the amount of time in seconds needed to make one full revolution of the wheel. Running this calculation, we get a period of about 0.001905 seconds.
That's fast.
Now remember, this is the time it takes the spinning mirror to make one full revolution. But in this experiment,
Need an
we're more
8.
concerned with the time it takes to make an 1/8 of the revolution, as this is the amount of time needed to let the beam of light move 35 kilometers there and 35 kilometers back. So we'll take our period and multiply it by 1/8 to get a time of 2.3810 times 10 to the negative 4 seconds.
That's
This is
fast,
our
right?
very fast time. Finally, we can use the uniform motion formula. The total distance will be 70,000 meters, since the light moved 35 kilometers or 35,000 meters one way and 35 kilometers back the other way.
And we're going to use a time of 2.3810 times 10 to the negative 4 seconds. Dividing these, we get a speed of light value to be 2.94 times 10 to the 8 meters per second, which is pretty close to the accepted value for the speed of light at 299,792,458 meters per second. Now you know how Michelson worked out the speed of light, but is that speed correct? How does he know that the speed is the same going forwards and backwards? Check out this Veritasium video. He does an amazing job talking about the one-way oscillator.
Skip ahead. Skip ahead. Go. Come on. There we go. All right. So that's how we determine the speed of light. Way to go, Michelson. All right. So now we're on to radio waves. Can you see radio waves?
No.
No. Can you hear the radio wave? Think about it. Not really. We use equipment that if you're going to listen to an actual radio, we use equipment that'll convert that to something you can hear. So the type of electromagnetic waves with the longest wavelengths and the lowest frequencies. Think about that for a second. Go back to this thing right here when I was saying, what's the relationship? So if you're always, if what you're dividing by is on the bottom and these two were on the top, if one goes up, the other goes down. If this one goes down, this one goes. So what kind of a relationship is that?
Gravity.
Oh.
You remember what it's called?
Inverse.
Inversely proportional. Good job, Emma. That's a good one. All right, inversely proportional. So the longest wavelength and the lowest frequency, go ahead, Eunice.
Radio wave.
Those are radio waves. All right. So if your frequency is low, your wavelength is long. Yeah, high. And if your wavelength is short, your frequency is there you go. All right. And if you think about it, if your wavelength is really long, then you're passing through that same point less often. So if your wavelength is long, your frequency is short. But if you're going like this, you're passing through it much more often, but you're going up and down, and the space between them is going to be smaller, right? So if you're going through the same point faster and faster, your frequency is faster, then your wavelength is going to be shorter. All right. So there are different types of radio waves. They all aren't used in your stereo. Radio waves are also used in MRI machines, which create images of the inside of the body. What's MRI stand for? All right, Carlos.
Magnetic resonance.
Magnetic resonance imaging. Anybody ever had an MRI?
Yeah.
Have you? What did you notice when you were in there? Anything in particular? Did they give you anything for your head when you went in there?
Oh yeah. It kind of.
What did
When he was in kindergarten and he split open his head on the.
Oh, that's fun.
Oh,
I went to the MRI.
They usually give you headphones.
Yeah.
Do you know why? MRI machines are loud, really loud, and it has to do with the magnets are shifting within the machine. There's actual magnets in there and they're shifting. So when you walk in the room, the last time I had one, I joked to them. I was like, gosh, you guys have dubstep all day. Because when you walk in, the machine's going, dooch, dooch, dooch. It's like disco. It's this really low sound.
You're not allowed to move.
Yeah, you can't move. And then when you get in, it makes all kinds of sounds. And it repeats these weird bumping, clanking, beeping, you know, it's a lot of like brrr, and that kind of stuff. It's really loud. So they usually give you headphones and you can still hear it.
It'd be nice.
The first one I had like 2 years ago, I had two of them back to back. And the first one I had, the lady's like, what do you want to listen to in your headphones? You're going to be in there like half an hour. And I'm like, I don't know. You have a just not really twangy country or really, really like hard rap, anything in between. I love like hip hop. She said, I recommend yacht rock. It's calming. I was like, yacht rock. Okay. So I'm in there and like Christopher Cross is playing and I'm chill. So when I went for the second one, she's like, what do you want to listen to? I said, yacht rock. She goes, that's interesting. I'm like, no, the other lady told me yacht rock. So microwaves. All right. Everybody has a microwave oven in their house. We usually just call it the microwave, but microwaves are what it produces. And those have what kind of wavelength? It has a high frequency. So Nico, yeah, short wavelength, high frequency. And they pass through certain substances like glass and plastic. So short microwaves are used in what? Which stands for radio detection. What's this? Radio detection and ranging. Darcy.
RDA.
Yeah, okay. Radar. All right. You hear the word radar all the time. You think it's a word. Radar. It is a word, but it's a word that comes from an acronym for radio detection and ranging. Radio detection and ranging. So it's radar. So radar is a word that comes exactly from what it
I
does.
just used the first letter of each of the.
Yeah, there you
words.
go, right? So when you put something in the microwave, you put in what kind of, you put it in glass or plastic, right? Or paper, right? But you can't, what don't you ever put in the microwave?
I
Metal.
put metal in a microwave once.
What happens if you put metal in the microwave?
It sparks.
It sparks. Okay, think back to what we just said about certain frequencies in the certain waves in the electromagnetic spectrum hitting metal and causing electrons. What does that sound like? Photoelectric effect. Ah, there's sparks coming off, right? Okay, so does anybody know how a microwave actually heats up your food? What does it actually do?
It has a bulb inside, like, and it produces like a really high amount of watts.
Yeah, that's more like your easy bake oven.
Oh, yeah.
Your easy bake oven has like 100 watt light bulb and it cooks your food with a light bulb, which is kind of wild.
Yeah.
A microwave. So we talked about how magnets and how magnets have polarity, right? There's a north and a south on a magnet. We're gonna be talking about this a lot more. You have a north and a south pole. That's why magnets repel some things and attract others depending on how you turn it, right? Okay, so the way a microwave works is there's magnets in it and they switch polarity. So they're switching north and south rapidly. They're alternating. Now, water molecules are what you call bipolar molecules, and we'll talk about this next year in chemistry. But water molecules have a charge that leans positive on one side and negative on the other. So what it's doing when a microwave is on, it's switching polarity and it's causing the water molecules to switch back and forth. They're physically moving. So what is heating the food? Friction. Your food is heated by friction. Yes.
I said friction.
That's it. Yes, because it's going right. So it's moving that water molecule. Yeah, that's how your food's heated. Isn't that weird?
That's interesting.
Yeah, it's friction. So infrared. All right. So infrared here are used as a source of heat and to discover areas of heat differences. You ever seen the videos of infrared or thermogram technology? That's when you get like it's dark. And we're getting there in a second here, but so infra means we said below, and then thermograms. All right, so this is like, you ever seen them? Oh, they have some good ones that are like nighttime police chases where they're looking from the helicopter and they turn on the infrared so they can see it produces what's called a thermogram. There's usually like, you can see the person that's running, but that person's like usually like a bright white color or sometimes a red color. And you can see them even though it's pitch black because it's sensing the heat. You ever seen that? You ever seen the footage of how they found the guy that was responsible for the Boston Marathon bombing? He was inside of a boat. He was hiding in somebody's boat in their backyard and they found him with thermogram.
Oh,
so it was
yeah.
infrared technology and they're like, there's a person under that boat cover in that backyard. And that's how they found him. That's where he was. But yeah, you can find all that with infrared and it's really cool. And sometimes you've seen it like where it's shades of color. It's like the red's the hottest part and then like the blue's the coolest part or whatever. You've probably seen that, right?
Yeah, because when you look in like there used to be this toy when I was like really young.
Yeah.
And my mom gave it to me and you could look through it and you could see like people's different body temperature.
Yes.
Yeah.
Same thing. That's what that is. So people use visible light to keep them safe, obviously, and to communicate. We use light to communicate. We use light for all kinds of things. So ultraviolet, we talked about briefly. It has applications in health, medicine, agriculture. So UV rays have very short wavelengths, shorter than visible light. And ultra means beyond. So ultraviolet is beyond violet light. So we talked about this a little bit ago. So small amounts of UV light are good for you, but too much can cause cancer, right?
Oh, that's not good.
Right. Yeah, not good. Not good at all. X-rays are used in medicine, industry, and transportation.
Too much.
They take pictures of the inside of solid objects. Who here has had an X-ray of some kind? Yep. Probably a dentist even. A dentist?
Yeah, dentists do actually.
Yeah, you probably got one at the dentist. They put those things in your mouth, make you bite down, put the thing up, it
Orthodontic,
goes beep.
yeah.
Yeah, right? Why do they if you go to the dentist and you're in the chair and they put that thing on your face, they cover you in a lead apron.
Yeah.
Why are they doing that?
So
they-
the
So they
letters
can't
in
like
your body.
see through you into your bones.
And then
stuff.
Yeah.
And then
To
they're
protect
gonna
the
see
food.
what's like the problem.
Yeah, they're not trying to avoid seeing into your body because they're aiming the X-ray detection stuff right at
It's
your teeth.
that you
They're
don't
trying to
get
keep the
cancer.
radiation off the rest of you
Mhm.
because too much X-rays can also cause cancer. So that's what they're doing is they lay it over you primarily your internal organs, but your reproductive organs they're trying to protect because those can really get affected by x-rays. So they'll just like flop it over your lap, and that lead, x-rays can't go through lead. So it stops them, the
Have you
block.
seen Daddy's Home?
I don't think so.
Oh, it's such a good movie. Basically, it happens to Will Ferrell, like the thing drifts
Oh.
down. Yeah.
Yeah, there you go. So x-rays have very short wavelengths and they can be used to see inside a body, but again, too much, not good. Gamma rays. All right, gamma rays are used in the medical field to kill cancer cells and to make pictures of the brain and industrial situations as an inspection tool. You know, when you go to the airport and they say, put your feet here and stand like this, and it goes whoop, whoop,
Yep.
gamma.
Oh, yeah.
That's gamma.
I
My mom has to.
I don't like that thing,
I've
but
been in
it's,
it once because they thought
Yeah.
I was like, they just pull random
Yeah.
people aside.
I don't dislike it because it's not dangerous. I just don't like the fact that so the person that's on site doesn't see your body, but somebody off site sees your body. And I don't like that. That freaks me out a bit.
Yeah,
But
I
they can
love
tell when things are off. Like I just, on Sunday, I went through the thing and the lady says, do you have anything in your back left pocket? And I'm like, oh my gosh, I do. I forgot that my hotel card was there. I'm sorry. And she just goes, I'm gonna touch you with the back. You know, so, but yeah, that's what that is. That's a gamma thing. So let's talk about some scientists. All right, so we've only got about 6 minutes. So this is a mentee for the older group, but for you guys, we're just gonna do some guessing. So we talked about William Herschel, right? So he pioneered the use of astronomical spectrophotometry. There's a word. Using prisms and temperature measuring equipment to measure wavelengths distribution of this is a good one, stellar spectra. So in the course of these investigations, he discovered infrared. So anybody want to take a guess for a year? Darcy?
1847.
1738. Way back in the day. This
Okay.
is before we were a country.
Yeah.
All right. Where do we think he's from? Eunice?
Germany. United States. Germany.
Germany?
English.
So he was
Yes.
born in Germany, which at the time was called the Holy Roman Empire. And then he moved to England when he was 19. All righty. How about, was he knighted?
Yes, he was.
yes, he
Sir
was.
William Herschel.
Yes, he was knighted into the royal. This is called the Guelphic Order, which is a Hanoverian order. Hanoverian meaning ties to German. Hanoverian order that broke ties with England when Hanover split off. And Hanoverians were a branch of German royalty. Okay. What was the biggest thing William Herschel ever discovered? This is a great question. You'd probably be surprised with this. What do you think?
Is it he discovered about the electromagnetic?
Oh, it's big. It's real big. This is a real big, it's a thing, an actual thing you can see, but it's big. What do you think?
The sun.
Not the sun.
No.
Lewis?
The moon.
No, we've been seeing the moon before
Rainbow,
1738. How about Uranus?
Yeah.
Ah, yes. So, and later, 2 of its moons. The first planet to be discovered since antiquity. So we're meaning since the ancient Greeks. We didn't know about anything that all the way up to the ancient Greeks. That's as far as we got. And then Uranus and Neptune came later. So he discovered something that nobody else had discovered. So he became famous overnight. All right.
Why did you name it Uranus?
Yeah, isn't it a great one? I'll let you look that up. All right. So
Okay.
what musical instruments do you think he played?
Trombone.
Trombone, guitar. All right. So he played oboe, violin, harpsichord, organ, and he composed 24 symphonies while he was doing astronomical spectrophotometry and discovering planets. He also composed 24 symphonies.
Wow.
This man was
Right. This man was definitely a polymath. Real quick, I'm watching him climb.
What's an oboe?
An oboe is a double reeded instrument. So like a clarinet has 1 reed, for example, or a saxophone has 1 reed. An oboe is a double reeded instrument. It's long. They're usually long and black. They play lower notes. They're a woodwind.
Oh, I think I've seen one.
There's a picture of it in there where I said, which musical instrument do you play? So there's our guy Herschel. All right. So here's Herschel.
Oh my gosh, spitting image.
And he can be found. There's a memorial for him in Westminster Abbey.
We would
And his marker is you may have seen it. So this right here, see this window? This is so cool. This is a memorial window at St. Lawrence's. And if you look, what's there at the top? There it is. So, yep. So they put in these planets for Herschel. That's a really cool stained glass window. Like a stained glass window full of astronomy is pretty awesome. So he has a quote. I have a quote from each of these guys. I'm watching. We've only got 3 minutes. I'm gonna try to roll through these. So when you can see, so this is what's on the memorial window, when I consider the heavens, the work of your fingers, the stars you've set in place, and that mankind, that you are mindful of him, the human beings that you care for them. That's actually a Psalm 8. It's a biblical quote that they put on the bottom of his memorial, which makes good sense. It fits. That's a fitting one, right? All right. So Young, let's talk about Young. So Young's the guy who established the wave theory of light, remember? And he had to overcome this century-old view of Newton's optics, which was that light's a particle, right? So we talked about that. So let's just go through these because I'm watching time. All right, we've only got 2 minutes.
38.
So he was born in 1773, so a little later than Herschel. He was
From
English. He went to Edinburgh Medical. Medical. Hold on, the guy that discovered that light is a wave was a physician? Here we go again with another polymath, right? And then University of Göttingen and Emmanuel College, Cambridge. So while a practicing physician, he spent 2 years as a professor at the Royal Institution. He taught philosophy. Hold up. Dude discovers that light is a wave. He's a physician and he teaches philosophy. So we have another polymath, right? Another polymath. How many languages? This is good. Are you ready for this? 14, fluent in, by the age of 14, he was fluent in 13. Okay, slackers. Who here speaks 13
I
languages?
speak.
Slackers.
I speak 2.
English, Greek. Okay, we've only got 1 minute. English, Greek, Latin, French, Italian, Syriac, Sumerian, Hebrew, Aramaic, Biblical Aramaic, Persian, Turkish, and Ge'ez, which is this is I believe it's like a South Indian. I looked it up. True or false? Young was instrumental in deciphering the Rosetta Stone.
True.
Do you know what the Rosetta Stone is?
Yes.
What's the Rosetta
It's
Stone?
that tablet thing.
It's a tablet that had something written on it in multiple languages. So if you knew what one language was, you could use it to decipher the other languages. He was also an expert in hieroglyphics.
Oh my.
Discovered that light is a wave, was a physician, taught philosophy, spoke 13 languages, and was an expert in hieroglyphics. Oh, anybody feeling a little like what's the word I want? Like you haven't quite accomplished enough in your life? Yeah.
Like 13.
So he is buried at St. Giles, the abbot, and he died after asthma attacks. And his autopsy showed he also had arthrosclerosis, which is the hardening of arteries. So he wasn't in great shape. Lastly, I'm going to zip through Michelson because it is 10:45. So just watch real quick. So this is the guy that said, oh, particle, right? All right. So no, speed of light. Sorry. This is the guy who did speed of light. All right. So he was born in 1852.
Oh, I was close.
He was from, born in Prussia, Germany, but he was American. All right. He attended a service academy. Service academies are West Point, United States Naval Academy, United States Air Force Academy, Coast Guard Academy. President Ulysses S. Grant awarded him a special appointment to be a midshipman at the U.S. Naval Academy. That's where my father-in-law went. So, true or false? Did he get a Nobel Prize in physics?
Yeah.
He did. All right. And his research partner was this dude named Edward Morley, who we're going to talk about. There, here's Michelson. This is where you'll find him today. We don't know where he is grave-wise because he had ashes and then we don't know what happened to him. And there he is hanging out with, oh yes, Einstein. So here's Morley real fast. Morley is 1838. He was from New Jersey. Yo, oh, Morley. Yeah, okay. So, yep, he went to this little place called Williams College in Massachusetts. No big fancy joint, right? He was a professor at Case Western Reserve and later Cleveland Medical College, and he taught chemistry. Okay. Discovered the atomic weight of oxygen. That's a big deal. Okay. True or false? He was an espoused atheist.
Yes.
No, he spent 3 years at Andover Theological Seminary and served a stint as a country pastor in Ohio.
Down in Ohio.
Yep. So here's Morley. We get actual photos of these guys when they get older. And this is some handwriting of him. He only outlived his wife by a few months. He died in surgery.
February 24th.
Last one, Roentgen. Okay, Roentgen is the guy, Wilhelm Roentgen discovered X-rays. Okay, you know my skeleton? My skeleton's name is?
Yeah.
Wilhelm? Okay, this is why. Okay, so he was born in 1845. He is from Prussia, which is Germany. Okay. He was educated at University of Zurich. That's in Switzerland. The first X-ray image ever seen was his own skeleton. He saw it, but he didn't like get a picture. He just saw it. Okay. First intentional X-ray. This is intentional. His wife's hand. And he was expelled from high school because he drew a caricature of a teacher and they were very offended. So they kicked him out. And he wasn't even the one who drew it. So there is an element named for him, and it's number 111 on the periodic table. And he did not become wealthy because he inherited 2 million Reichsmarks from his father's death. And for ethical reasons, he did not seek patents for any of his discoveries because he thought they should be publicly available without charge. So he was kind of independently wealthy. And this is super cool. Right here is a photograph. If I can get it, here it goes, somewhere in here. That is his wife's hand.
Oh, what is that?
I think it's a ring
It's a ring.
on Anna Bertha's hand. So that's his wife's hand. Yep. All right, so we got to get the other group going. We won't have time for Hertz, but take a look at Hertz. Hertz is interesting because real quick, if you see this date, 1857, and you know he was German, that tells you something probably about what his life might have been like. Because think about what happens in Germany about when he's probably about 50-ish.
Yeah.
Nazis. Okay, yeah, there we go. All right, if you guys would tell the other folks to come on in, that would be super.
Darcy, do you want to know the two languages? Come on, Evo.